Welcome to This Explainer. I'm absolutely thrilled you're joining me today because we're tackling something that is literally the backbone of mechanical engineering, motorcycle chassis design. Now, we aren't just talking about making things look cool. We are diving deep into the actual real-world math that keeps riders alive. Specifically, we're going to break down the exact calculations you need to figure out the correct pipe diameter for a bike frame. By the time we wrap up, you'll understand the hidden numbers holding the whole shebang together. Okay, let's jump right in. So, ask yourself, will a 2G impact break your bike frame? That is the high-stakes reality we're dealing with. Think about it. When you're cruising down the road and suddenly, bam, you hit a massive pothole, drop off a curb, or land a jump, your frame takes a massive, instantaneous hit. The math we're going to look at isn't just some boring textbook theory. It's a literal life-saving tool. It's designed to stop catastrophic frame failure right in its tracks at highway speeds. We've got a design for the absolute extremes, not just those nice, smooth Sunday rides. Section 1. The bike load problem. Let's calculate the total weight. All right, before we can even begin to figure out how strong our metal needs to be, we have to establish a baseline. What exactly are we asking this frame to carry? Well, the starting point is actually surprisingly simple. Let's break down the specific static weights. We're looking at an assumed bike weight of 130 kilograms. That covers your engine, the wheels, the fuel, all the components. Then we toss on a standard rider weight of 80 kilograms. Add them up, and that gives us a total static load of 210 kilograms. That right there is the baseline mass the frame has to support when it's just sitting perfectly still in your garage.
But here's the thing. Engineering doesn't operate purely on mass. It operates on force. So we've got to do a quick, necessary conversion. We take that static mass, our 210 kilograms, and we convert it into a base gravitational force. When we factor in gravity pulling everything down, that 210 kilograms exerts roughly 2,060 newtons of force straight into the ground. That 2,060 newtons, that's our baseline resting force. Basically, it's the calm before the storm.
But remember that severe bump we just talked about? Let's see what happens when the bike is actually in motion. During a 2G condition, like hitting that pothole at high speed, the force doesn't just sit at the resting baseline. No way. It multiplies dramatically. Our 2060 newtons instantly doubles, slamming a massive 4120 newton force directly into the frame. This is the dynamic load we actually have to design for. I mean, if we only built the bike for its resting weight, the thing would literally snap in half the first time you took it down a rough road. And honestly, we have to keep the crazy physical reality of riding in mind. That 4120 newton vertical smash, it's not the only enemy out there. At the exact same time, the pipe has to endure twisting torsional loads when you lean hard into a corner, bending loads from how the weight is distributed, and constant fatigue-inducing vibrations from the engine and the asphalt. The metal is under this constant chaotic attack. Kind of like a standard Tuesday commute, right? Section 2, calculating bending moment. Let's look at how force attacks the metal. So we know the force is 4,120 newtons. But how does that force actually mess with the geometry of a chassis? Well, to make the math manageable, engineers use conceptual models. Enter the Simply Supported Beam, or SSB for short. Imagine we isolate a critical 500 millimeter length of chassis pipe. We model it as just resting on two supports, say representing two structural nodes on the frame, with that entire 4,120 newton force pushing straight down from the top, right dead center. Simplifying the complex chassis into this 500 millimeter SSB model, that's what allows us to reliably nail down the exact bending forces at play. Okay, let's walk through the bending moment math together. It's not too bad, I promise. We take our 4120 newton force, we'll call that W, and we multiply it by our 500 millimeter length, that's L. Using the standard formula, we just divide that product by 4. And what do we get? We get an absolutely crucial massive figure, 51,500 newton millimeters. That number right there is the maximum twisting energy trying to snap our pipe right down the middle. Section 3, section modulus and stress. This is where we find the material's breaking point. Now that we know the exact mechanical burden crushing down on the frame, we've got to connect that calculated physical force, our 51,500 newton millimeters, to the physical geometry of our steel pipe. The absolute key here is understanding stress. And stress in engineering is exactly what it sounds like. It's a measure of how much the metal is agonizing under the load. To figure out if our frame survives, we have to take our bending moment and divide it by the pipe's unique section modulus. Think of the section modulus as a geometric property that just tells us how much resistance a specific shape has to bending. Check this out. Here is the exact formula for the section modulus of a hollow round pipe. Now, I know the pi and the powers of 4 might look a little intimidating at first glance, but notice what this property actually cares about. It is entirely reliant on the inner and outer diameters. That's it. The thickness of the pipe wall is the ultimate make-or-break deciding factor in whether the pipe bends, completely breaks, or holds strong.
Section 4, Finding the Pipe Diameter. It's time to put the math together.
We have finally reached the climax of this explainer. This is where all those abstract equations turn into real-world physical metal you can hold in your hands. Let's pull all our knowns together. We've got our calculated bending moment of 51,500 Newton millimeters. We've chosen our material, cold-worked or CW steel pipe. And crucially, we have to introduce the yield stress limit for this specific steel, which is 340 megapascals. Now, yield stress, that is the exact threshold where the metal stops springing back and permanently bends. We absolutely cannot, under any circumstances, let our pipe's stress exceed 340 megapascals. If we do, the bike frame is permanently ruined. Game over. And honestly, this right here brilliantly illustrates the pure elegance of engineering. By slotting our maximum allowable yield stress of 340 megapascals, along with our structural bending moment of 51,500 Newton millimeters, straight into our stress equation, we only have one set of variables left to figure out: the geometry. From here, we can easily solve for the required outer diameter and inner diameter. It's basically a giant puzzle. If we pick an outer diameter we want just for the cool look of the bike, the math steps in and dictates exactly what the inner diameter, and therefore the wall thickness, has to be. It guarantees the stress stays below 340 megapascals, keeping the rider completely safe. You know, it's incredibly empowering when you realize that the safety of a high-speed vehicle boils down to such logical, structured math. There's no guesswork here. So I'm going to leave you with this final thought. Are you ready to calculate the perfect pipe dimensions for your next custom build? Because whether you're a hardcore engineering student or just a DIY gearhead tinkering in the garage, you now have the exact step-by-step logic to ensure whatever you build will not buckle under pressure. Keep calculating, stay curious, and hey, thanks so much for exploring this awesome topic with me today.